All right, are you cramming for a big chemistry exam, or maybe you just need a super fast refresher on some concepts that can be, let's be honest, kind of tricky? Either way, I've got you covered. We are about to break down some of the toughest topics from Unit 2 chemistry, so let's just dive right in. Look, redox reactions, cell diagrams, nuclear stability, these topics can feel like this huge, tangled web, right? It is so easy to get lost in all the little details. But our goal here is pretty simple. We're going to give you a clear map, a guide, so you can navigate all these ideas with total confidence. So here's our game plan for today. We're kicking things off with the absolute foundation, redox reactions. Then we're going to immediately use that knowledge to calculate cell potential. From there, we'll get visual and learn how to see these systems with 3 essential diagrams. After that, we'll zoom right into the core of the atom, the nucleus, and we'll wrap up by uncovering the secret to what holds it all together. First stop, redox. Getting this part right is absolutely fundamental. Why? Because everything we talk about after this, from how batteries work to nuclear chemistry, it's all built on this one simple idea, the exchange of electrons. This slide really just cuts right to the chase. It's a perfect side-by-side comparison of the 2 halves of every redox reaction. So oxidation means an element loses electrons, and because it's losing negatives, its oxidation state goes up. Reduction is the total opposite. It gains those negative electrons, so its oxidation state goes down. Simple as that. It's always a pair. One thing loses, another thing gains. Okay, so now that we've got a handle on how electrons are moving around, let's actually put that knowledge to work. We're moving into the practical stuff, calculating the electrical potential of an electrochemical cell. This is where the numbers start to come into play. And here it is, the key formula you absolutely need to know. The standard cell potential, we call it E0 cell, is just the potential of the cathode minus the potential of the anode. Honestly, the entire challenge here boils down to just one thing. Can you correctly identify which one is the cathode and which one is the anode? Which, of course, leads to the million-dollar question every single chemistry student has asked at some point. You're staring at one of these cell diagrams and it looks complicated. Where do you even begin? How in the world do you tell the anode from the cathode? Well, here's an incredibly powerful memory aid, and it's a real game changer. LOAN. L-O-A-N. This tells you exactly how to read a cell diagram. The component on the L side, that's where oxidation is happening. And that means it's the anode, which carries the negative charge. Just remember LOAN, and I promise you will never mix them up again. So we've got the formula down, now let's level up and get visual. We're about to break down the 3 key diagrams that chemists use to actually visualize and really understand these complex redox systems. First up, we have the Latimer diagram. The best way to think of this is as a concise summary. Its whole purpose is to show you, just at a glance, the standard electrode potentials as an element shifts from one oxidation state to another. Now, to read or build one of these, you just need to know 4 simple rules. 1. All the reactions are written as reductions. 2. Because of that, the oxidation states always go down as you read from left to right. 3. If you ever need to find a potential that isn't already on the diagram, you have to use the Gibbs free energy equation. That's the master equation that connects it all together. And 4. Just to keep things clean and simple, water, protons, and electrons are always left out. Next up, the Frost diagram. This one is all about one thing, stability. It's a graph that plots Gibbs free energy against the oxidation state. So here's the key takeaway. The lower a species sits on this graph, the more stable it is. It's a really quick, visual way to compare how stable different forms of an element are. And our third and final diagram is the Porbes diagram. What makes this one so powerful and unique is that it adds another variable to the mix, pH. By graphing potential against pH, it shows you which form of an element is the most thermodynamically stable under all sorts of different acidic or basic conditions in water. All right, we spent a lot of time talking about electrons, so let's shift our focus and go right to the heart of the atom, the nucleus. We'll start off by breaking down the 3 key ways we classify and relate different nuclei to each other. This table lays it out perfectly. First, you have isotopes. Think carbon-12 and carbon-14. They have the same number of protons but different numbers of neutrons. Next up, isobars. They have the same total mass number but a different mix of protons and neutrons inside, like argon-40 and calcium-40. And finally, you've got isotones. These are atoms that share the exact same number of neutrons, like boron-12 and carbon-13. So we know what the nucleus is made of, but what is actually holding it all together? What keeps it from just flying apart? That brings us to our last and maybe most important topic, the secret behind nuclear stability. And it all comes down to a really critical balancing act. So what does it take for a nucleus to be stable? Well, three things. It needs a high nuclear binding energy. That's basically the superglue holding it all together. Also, pretty much by definition, a stable nucleus won't just fall apart or change on its own. But the most critical factor, the one that really governs everything, is that neutron-to-proton ratio, the N/P ratio. And this is where it gets really interesting. For the lighter elements, we're talking a mass number under 20. Stability happens when the number of neutrons and protons are about the same, so ratio close to 1. But as nuclei get heavier and you start packing more and more of those positively charged protons together, you need extra neutrons to act as a buffer. For these big, heavy elements, stability actually requires an N/P ratio that's greater than 1 just to overcome that powerful repulsion between all the protons. Wow, we've covered a ton of ground, haven't we? From the simple flow of electrons all the way to the forces holding the nucleus together. We've seen what makes a nucleus stable, but that leaves us with one final, lingering question. When that delicate balance is off, when a nucleus is unstable, what happens next? What path does it take to finally find stability?